Hello there, this is Aditya, and you are here to learn graph data structure. So, we are going to dive head on into this data structure. Before we start, let's forget about the coding aspect of it and try to understand what basically a data structure graph looks like and what is the idea behind it. So, graph has when we talk about graph, it just has two things that make the entire data structure. One is the vertices. So let's say we have the vertices, the first vertex as V1, and we have another vertex V2. Now these two vertices are separate and they don't do a lot or anything by themselves. The other thing that makes the graph data structure other than the vertices, so we have the vertices. The other thing are the edges. So the edges can be like unidirected or they can be bidirected. So let's look at first the unidirected. So this is the unidirected edge between V1 and V2. And the arrow, the significance of arrow is that if you are supposed to travel from a vertex V1 to V2, the entire idea of graph is to travel from one vertex to another. And so if there is an edge which is unidirected between two vertices v1 and v2, and if you are looking to travel between the vertices, this arrow says that you are only permitted to travel from v1 to v2, not otherwise. You cannot come back from v2 to v1. And the other case is that if we have like similarly two vertices and we have bidirected edge between them, what this signifies is that you can go from v1 to v2, you can reach from v1 to v2, and you can also reach from v2 to v1. So these are the two types of edges that we will look at in graphs. So we call them as directed graph and undirected graphs. But since we are talking about graphs and directed graphs, let's to to say like we have anything that has edges and vertices is a graph. So now on paper, what a graph looks like is very understandable, right? We know what a graph data structure looks like on the paper. We do not have any idea how we code it or how it looks from the programming aspect, but we know now we have the understanding of how it looks on the paper. And since we know how it looks on the paper, it's a good time to discuss its applications. Like we have vertices, we call them vertices or nodes, and we have edges. What's the significance? Like it has a huge significance, right? So like these are the users on a social media app, right? This is a social media app, let's say, and I have one, two, three, four, five. So I have like five users, right? Six users, including zero. And these social media app, these are not friends. So there is no, let's say two is friends with five, right? And one is friend with zero, four is friends with three. And so what it does is we have direct links between 0 and 1. So maybe we can use this data structure to program that, yes, since 0 and 1 has an edge between them, they can look each other's profile and text each other. Since 1 and 2 do not have any edge between them, right? So they are not permitted to text each other. So that is the use of some sort of real application of graph that we look in practical world, practical applications around us. So it is a powerful data structure, and it's fun to work with. Personally, I enjoyed a lot programming in graphs, and it is a fun data structure. It's not too hard, believe me. So do not try to, at this point, do not try to come up with the coding or try to get a little uh, get a little discouraged about how we are going to code it, because it's, believe me, quite simple. Just let's just stick to how and everything about on paper how a graph looks like. Now Since we are also talking about graph, it is a good time to also talk about graphs versus trees, right? So when I talk about trees, everyone must be having an image come up to their mind, which is some sort of like this. So what a tree is, we have a root and parent, this will be the parent node, and it has two children in this case. And for this parent, it has two children. So interestingly, we can access the children from the parent, but we can never access the parent from the children. So tree is a directed graph, right? We observe that we can go from parent to its children, we can reach out to the children, but the children cannot reach out to the parents. So tree is nothing but a directed graph. So yeah, tree is a subset of graphs, but it's not like every directed graph is a tree. And this is over here, that image that pops up on our mind is not just a tree, it's a binary tree. The moment I add more than two children to a parent, it is no more a binary tree, but just a tree. So if we have a tree which is directed and acyclic, right? If it is acyclic, in the sense, mm, just in the sense there is no cycle on the graph. Like this is a cycle. If I connect an edge like that, this becomes a cycle. So if that's not that's not on the graph. So if it is an acyclic directed graph, and we have vertices, that is nothing but nodes, equal to n, and edges equal to n minus 1, right? So this kind of graph is always a tree, and that we can observe that over here. How many vertices do we have? 1 2 3 4 5 6 7 8 9 10. We have 10 vertices, and edges 1 2 3 4 5 6 7 8 9. We have 9. That is nothing but 10 minus 1, right? So that is what a tree is. A tree is nothing but an acyclic directed graph with n number of vertices. With For n number of vertices, it has n minus 1 edges. And another interesting thing, or another one liner to say how tree is related to graph, is for a graph, for any graph, if there for all the pair of two nodes on the graph, like if I take any pair for any two nodes, any two random nodes on the on the graph, if there exists a unique path, right? So I'm going to consider bidirectional uh, for this path, finding the path. So if there exists a unique path, it is a tree for every two nodes, for every any two nodes on the tree. So that is what the other statement can be like, for any two nodes, and these two nodes can be any on, that is like for every any pair of two nodes on the graph, if there exists a unique path for every any two pair of nodes, it will be a, a tree. So I hope you get the point what I am trying to say. If not, just stick with acyclic directed graph with n vertices and n minus 1 edges is nothing but a tree. So that is the similarity that we have between graph and trees. Again, now that we have this, let's move on to how we traverse a graph and what does traverse means. Now, the entire purpose of developing a graph is to reach out to data very efficiently. So let's say we have a graph like this, and we have the starting point as this. We are starting over here. So how do we traverse the graph? Like how we explore every node on the graph? Like we are here and we want to explore the entire graph. How do we do that? The first way is to like just reach out to a node or another node from the starting point, and then again do the same with that node. So I reach out to here, from here to here. Then now I cannot reach out to any new node, so I come back. Now from here I cannot reach out to any new node, I come back, and now I will reach out to the another new node over here, and then I will reach do the same for this node. I'll reach out to here. Now from here I cannot reach out to any new node, I'll come back. Then again I cannot reach to any new node, I'll come back, and then I'll try to reach out to a new node, new vertex. These two are over, so this or either this, I chose this. And from here I'm going to try to reach out to some new another new vertex. So there is a possibility, and that is this one. From here I cannot reach out to any new vertex, so I'm going to come back. Again, no possibility, come back, and here, and then here, come back, come back. And since I cannot reach to any new vertex, I've actually explored the entire vertices on the graph. So this is nothing but depth first search. What we do is we take one path, like what we did is, if you observe what we did, we started from here, we took one path and we continued down the lane, then we came back, and then we pick a route and we just go to the deepest possible level. So if this is the depth 1, this is depth 2, we try to get to the deepest um, node on the random path we chose, and then we come back and do the same for all the nodes. So that is how a depth first search works. The other alternative that is very popular is breadth first search. This is just, we are talking on a high level. When we will code, we will look into it very with a very magnified vision and try to understand everything. But I think it is a good idea to start developing an idea of how the traversals work. So this is again the starting point, and this time we are going to do breadth first search. So breadth first search name comes from the tree data structure over a graph which is actually really a mess. Breadth doesn't make sense anymore because there is no length and breadth. Graph can be like a very messy data structure. So what we do is, the idea is to iterate over the near, like this is like the first depth from the start, right? So the idea is to visit this and keep it in memory, visit this, keep it in memory, visit this, keep it in memory. These are all depth 1. And visit this, keep it in memory. Now when we are exhausted, we do not have any vertex which is at a distance of 1 from the starting point. What we do is, we had stored them in the memory, now we pop them out of the memory and try to explore them, right? So we what we do is, we reach out with all the nodes which are at a distance of 2 from the starting point, right? So this 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 so you see, the idea is, like in the depth first search, um, what we do is we start with 1 2, try to maximize this number as we go down the line, and then come back and try to again maximize, like we are going in an incremental order of depth. Whereas in breadth first search, what we are doing is, we are proceeding radially, right? Like we are first exploring all the nodes which are at a distance of 1 from the starting point, then we are increasing our radii by another 1. So now we are going to try to explore all the nodes which are at a distance of 2 from the starting point. So you get the idea, right? The difference between depth first search and breadth first search. And uh, all this means nothing if we cannot actually do the coding, right? So next on, let's move on to the coding aspect of graph, where we will actually write the code to build the graph data structure, and where you will realize it is not as complicated as it looks or as it feels while